Okay, hello. So my mechanism is the red one, and I'll start off by describing the clues and looking at our reaction. So we start with a cyclic amide, and then we end with a deprotonated carboxyl and a protonated amine. The first clue says that we have only two residues in the active site, which means that it's a catalytic dyad, and both of them appear to be aspartic acid. Then we look at our second clue, which is the pH profile. It seems to be most active at around a pH of 4, which is pretty close to the pKa of aspartic acid, which is 3.7. So this means that one of our residues is acting as a base up here, and the other one is acting as an acid down here. And yeah, it's most active at around a pH of 4, which is in between those two pHs or pKa's. So looking at our first step, I want to first recognize that the catalytic strategy of proximity is used here. These two aspartic residues have to be close to each other in the catalytic dyad and also close to the substrate. So in the first step, our aspartate will act as a base and grab the hydrogen on the aspartic acid, which will then push the electrons in the bond between O and H to the oxygen in the carboxyl group. And that will cause the oxygen in the carboxyl group to become partially negatively charged and become a nucleophile. And so then the electrons there will attack this electrophile, the carbon of the carbonyl electrophile, and that will push the electrons in the double bond to the electronegative oxygen. Then going to our next step, the catalytic strategy of an oxyanion hole is used here because our oxygen has a negative charge and we want to stabilize that with a metal cation such as zinc. So in our second step, we'll push the electrons on this electronegative oxygen, or discharged oxygen, into the double bond again, and we'll try to kick out this nitrogen. However, it's not really a good leaving group, so we'll grab the hydrogen on the aspartic acid and kick the electrons in the OH bond back to the oxygen. Then in our next step, water will enter. In this step, the aspartate will act as a base and grab a hydrogen on the water and then push the electrons in the OH bond back to the oxygen. Then it will attack the electrophile of the carbon in the carbonyl group and push electrons in the double bond back to the electronegative oxygen. In our next step, we have a tetrahedral intermediate, which shows covalent catalysis because later that will be broken. And again, we want to push the electrons in the charged oxygen into a double bond, and we'll try to kick out the aspartic acid residue this time. And we also want to reference the beginning, which shows us that there's a protonated amine, and one of the aspartic acid residues is deprotonated, and we want to restore that. So this amine group here will grab the hydrogen on the aspartic acid, and we'll kick those electrons in the OH bond back to the aspartic acid residue. And so that gives us our deprotonated aspartate and our protonated amine. The next thing we want to do is have a protonated aspartic acid and have a deprotonated carboxyl group. So that's what we'll do here. Our carboxyl group will grab the hydrogen our carboxyl group on the aspartic acid residue will grab the hydrogen on the carboxyl group of the substrate, and then so the electrons in the OH bond will go back to the oxygen. And that will give us our deprotonated carboxyl group, our protonated amine, and one protonated and one deprotonated aspartic acid residue. To sum up our covalent strategies, we have proximity here, we have an oxyanion hole, and we have covalent catalysis with bonds being made and broken, and we also have an acid here and a base. Oops, I said that backwards. I mean a base and an acid. Thank you for watching.